Unlock the power of real-time grid protection with dynamic system monitor panels. Engineer Sharif Hussain presents a comprehensive utility-level technical course, diving deep into the future of power system stability and analysis. DSM panels are advanced monitoring systems for power grids, capturing high-resolution dynamic data to analyze events like faults, oscillations, and stability issues in transmission networks operating at voltages from 40 kilovolts upwards. Dynamic measurements refer to time-synchronized, high-speed recordings of electrical quantities such as voltage, current phasors, frequency, and rate of change of frequency, typically at 10 to 60 samples per second, contrasting with slower SCADA data. Primary goals include rapid disturbance detection within milliseconds, stability analysis covering transient, voltage, and frequency, and enhanced situational awareness to prevent blackouts, like the 2003 U.S. Northeast event. DSM panels are deployed in high-voltage transmission lines, control centers, substations, and renewable integration points like wind farms, handling connections over 100 megawatts. Focus areas emphasize DSM for synchrophosors, stability controls like transient control automation, and capturing fault waveforms with subcycle resolution, crucial for 60 Hz systems. The operating principle utilizes synchrophosor technology, where phasor measurement units, or PMUs, measure sinusoidal waveforms and timestamp them via GPS for precise grid-wide synchronization. Measured parameters include phasor magnitude, phase angle, frequency, and Rohkopf, with voltage ranging from 1.0 to 1.1 per unit and frequency between 59.5 and 60.5 Hz. PMUs are IEEE C37.118 compliant devices, providing positive sequence phasors with 1 millisecond accuracy timestamps, directly referenced from GPS satellites. High accuracy is achieved through GPS-disciplined oscillators, ensuring microsecond-level time alignment across grids spanning over 1,000 kilometers, with a total vector error less than 1%. Sampling rates range from 10 to 60 frames per second, with 30 frames per second being standard for capturing 16.7 millisecond cycles in 60 Hz systems, enabling oscillation detection up to 2 Hz. The DSM panel architecture is modular, comprising PMUs, fiber optic data communication, central processing units with 16-plus cores, redundant servers with over 10 terabytes of storage, and dual power supplies. Panel units feature a layered design, a top visualization HMI with 22-inch touchscreens, middle communication modules, data concentrators, and bottom power distribution units. Communication networks support IEC 61850 Goose and SV protocols for sub-millisecond latency, DMP3 for SCADA integration, and TCP/IP Ethernet for wide-area networks up to 10 gigabits per second. Data concentration and processing aggregate streams from 10 to 50 PMUs, performing quality checks like signal-to-noise ratio greater than 30 decibels, filtering, and compression using C37.118.2. Visualization through HMI dashboards displays real-time frequency deviation maps, angle difference plots up to 180-degree separation alarms, and dynamic oscillation animations. Oscillation detection and analysis utilize modal analysis, such as the Prony method for modes between 0.1 and 2 Hz, and spectral analysis with FFT up to 10 Hz resolution for inter-area oscillations. Stability monitoring tracks transient stability with rotor angle swings below 180 degrees, voltage stability using PV curves, and frequency nadir, maintaining a minimum of 59.3 Hz post-disturbance. Event detection provides automated alarms for low-frequency oscillations below 0.5 Hz and faults with current exceeding 2 per unit, with event reporting within 100 milliseconds. Integration with energy management systems and SCADA feeds data for state estimation every 20 milliseconds, significantly enhancing contingency analysis compared to 1-minute SCADA updates. Cybersecurity features include EES, 256 encryption, role-based authentication compliant with NERC CIP 007, firewalls, and intrusion detection for operational technology networks. Commissioning tests verify PMU accuracy with total vector error below 0.5%, time synchronization error less than 1 microsecond, and end-to-end latency under 100 milliseconds using test sets like Doble F6150. Maintenance involves regular firmware patches quarterly, data integrity verification through CRC checks, and automated backups to cloud storage like AWS S3. Advantages include improving grid stability by 30 to 50% through early detection, reducing outage durations from hours to minutes, and supporting renewables penetration up to 50%. DSM panels adhere to international standards such as IEEE C37.118 for synchrophosphors, IEC 61850 for substation automation, and NERC Mod 32 for PMU data use. A case study from a 40 kV interconnection project in Egypt in 2022 demonstrated DSM detecting a 0.8 Hz oscillation, successfully preventing a cascade failure in a 200 MW renewable tie-in. Optimal PMU placement is crucial at bisection points for synchronism and angle monitoring, with redundancy of 2 PMUs per line and ensuring 99.99% availability. Future developments include integrating AI and machine learning for predictive analytics, achieving 95% accuracy in anomaly detection, and implementing wide-area control systems for automated damping. In conclusion, DSM panels provide critical insights for smart grids, enabling deep learning-based optimization and resilient power systems for the future. Follow me and share the video for engineering made simple.